P-H-Y, 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 P-H-Y. Physics. Welcome!
Welcome to another AP Physics Camp lecture. Today we're going to be discussing two-dimensional motion. Yes, Alex, something like that. Angry Birds is a good example of two-dimensional motion, where the object is experiencing projectile motion, which is exactly what we're going to be reviewing in today's lecture. So make sure you take good notes and let's begin. Before we start, it's important that we understand what two-dimensional projectile motion is. You're right, Alex. Two-dimensional projectile motion is referring to an object that is being thrown into the air, which we refer to as a projectile, such as that football that you just threw. Yes, Alex, a baseball would also act as a projectile. Or even an Angry Bird, but you might want to ease off on the Angry Bird games because I think you're playing way too much. Nevertheless, these projectiles follow a trajectory path such as this one, in which it could be broken down into vertical and horizontal components of motion. Yes, that's right, Alex. Because we will be dealing with vector components of motion, we will also be dealing with resultants, which means, yes, Alex, you guessed it, we're going to be working with the Pythagorean theorem, right triangles, and SOHCAHTOA. But before we start diving into vectors again, it's important that you understand that two-dimensional projectile motion can basically be broken down into two separate one-dimensional motion problems. Yes, Alex, I guess that's one way of seeing it, the two representing two problems consisting of the object's horizontal motion, in which we say is the x component, and the other is the vertical motion, in which we say is the y component. Yes, that's right, Alex. Projectiles such as this toy car will follow this trajectory in the air while experiencing constant deceleration due to gravity, which can be rounded as negative 10 meters per second squared. However, since we said that we're going to be breaking down this object's projectile motion into two components, the horizontal and the vertical, then my question is, what component would experience the constant deceleration due to gravity? So think about what acceleration due to gravity is. You got it, Alex. In other words, acceleration due to gravity pulls down, meaning that the vector would be on what axis? That's right, Alex. Acceleration due to gravity is a vector on the negative y-axis, which is why we're going to label it as AY equals negative 10 meters per second squared. Okay, so let's think about it. Does acceleration due to gravity point in any way on the x-axis? That's right, Alex, it doesn't, which is why we label AX as 0 meters per second squared. Great way to sum it up, Alex. AY equals negative 10 meters per second squared, which means that the vertical velocity is changing every second by 10 meters per second. Now, as for the AX, it equals 0 meters per second squared, meaning that the horizontal velocity doesn't change. Yes, Alex, I guess you could say that. Since vertical acceleration, which is due to gravity, will not change, it remains constant. And as for the horizontal acceleration, despite it being zero, it will not change either. So yes, both vertical and horizontal accelerations are constant, which means, that's right, Alex, since the accelerations are constant, we can use the kinematic equations, which is why these equations can also be broken down into vertical and horizontal components. Notice how the horizontal component equations simply have an x subscript to signify that you are working with horizontal motion components. Now, as for the vertical motion components, these equations now have a y subscript. You got it, Alex. Delta x and delta y are simply used to distinguish between horizontal and vertical displacement. Good question, Alex. Time is the only variable that is not broken down into components because it's not a vector, which means that time is the same for both vertical and horizontal components. Yeah, I guess you could see it that way, in which time is the variable that links our two component problems since they're technically occurring at the same time. Okay, Alex, enough mind-blowing breakthroughs, and let's get back to tracking our toy race car's two-dimensional projectile motion. Okay, let's say that a toy race car is launched with an initial velocity of 3.7 meters per second at an angle of 15 degrees above horizontal from its launching ramp, that is 1.5 meters in height. What distance from the table should you place your toy bin to catch the toy car? How long will it take to get there, and what was the final velocity? That's right, Alex. We must first list out our variables. Now we must identify if we are given resultants or components. That's right, Alex. This would be our y component for displacement. So let's write them out in blue for vertical. Right again, Alex, we want to know the x component for displacement. So we're going to write that in red for horizontal. Right again, Alex, time is not a vector, which means that it does not have components. In other words, it's the same for both. Great job, Alex. The initial velocity given is the resultant vector since it is at 15-degree angle. Now remember, we want to break down this two-dimensional problem into two one-dimensional problems, which means we need to break down this resultant into the vertical and horizontal component. So how do we do that? You got it, Alex. Since we only know one of the sides from this triangle and the angle, we can use SOHCAHTOA. But which function do I use first? Great idea, Alex. We must label our triangle sides as opposite, adjacent, and hypotenuse based on the angle given. Now notice that this means that our opposite is the y component, the adjacent is the x component. Okay, Alex, let's start with the vertical initial velocity in which y component is the opposite side of the triangle. So we should use That's right, Alex. We should use sine theta equals opposite over hypotenuse, in which we are solving for opposite since it represents vertical initial velocity. Let's move the hypotenuse, which represents the initial velocity, to the other side by multiplying it on both sides. This results in the following equation, in which sine of 15 must be multiplied by 3.7 meters per second to determine what the vertical initial velocity is. Great job, Alex. Our initial vertical velocity is 0.95 meters per second. Now let's solve for the initial horizontal velocity, which we said represented the adjacent side of the triangle. Therefore, we must use Right again, Alex, we must use cosine theta equals adjacent over hypotenuse, in which we are solving for adjacent since it represents the horizontal initial velocity. That's right, Alex. We must move the hypotenuse, which represents the initial velocity, to the other side by multiplying it on both sides. This results in the following equation, in which cosine of 15 must be multiplied by 3.7 meters per second to determine the horizontal initial velocity. Great job, Alex. Our initial horizontal velocity is 3.57 meters per second. Okay, now that we've listed out our displacement and the initial velocity components, it's a good idea if we organize them into two lists, one for the horizontal components that will be written in red and one for the vertical components that will be written in blue, so that we can make sure that we solve for the missing variables using the right components. Good job, Alex. We're looking for time, final velocity, and delta x. Let's start with final velocity because I want you to notice that the problem is asking for the final velocity when it hits the toy bin. Therefore, we're actually looking for That's right, Alex, we're actually looking for the resultant final velocity. So first we must determine what we already know about its components. Great job, Alex. We know that the horizontal final velocity is the same as its initial horizontal velocity, since the horizontal acceleration is 0 meters per second squared. Okay, what about the vertical final velocity? How do we figure this out? You're right, Alex. There was a vertical acceleration due to gravity. Therefore, the velocity did change. So we actually need to use one of our kinematic equations here to solve for it. But which one? Good job, Alex. If we highlight our known and unknown variables, it becomes much easier to find which equation is the right one to use. And in this case, we can use this equation since we know all of these variables except final vertical velocity. That's right, Alex. Now that we have completed step 1 and 2, we must now plug and solve for the missing variable to complete step 3. And in this case, this results in the final vertical velocity of 5.56 meters per second. Now that we know both the vertical and horizontal components of final velocity, how do we figure out the resultant? Great job, Alex. Since we have two sides of a right triangle, we can now use the Pythagorean theorem to determine the missing side, which is our resultant vector. Okay, let's plug in our values and solve for c, which results in a final velocity of 6.6 meters per second. Okay, next let's determine how much time it would take for a toy car to land on the toy bin. We can do this by using our first kinematic equation, which says Next, we need to do step 3, which means that we must rearrange the formula to equal t, in which we must subtract final vertical velocity and initial vertical velocity, then divide it by acceleration. Yes, Alex, that's right. After plugging in the values and solving for time, t equals 0.46 seconds. Okay, next let's solve for the distance that the projectile will travel from the table. In other words, the horizontal displacement, which is delta x. Yes, that's right, Alex. We can use this kinematic equation to solve for delta x. All we need to do is plug in our values and then solve. Now, notice, we see that 1/2 at squared results into 0, since horizontal acceleration was 0, which means that we're actually only left with delta x equals horizontal initial velocity times time, resulting in 1.62 meters as the horizontal displacement. Okay, Alex, here are some bonus questions. What was the maximum height that the projectile reached? Good job, Alex. We know that the final velocity at the maximum height of this projectile was 0 meters per second. And we know its initial as well as its vertical acceleration due to gravity, which means that we can solve for delta y by using this equation. That's right, Alex. We must rearrange the formula to solve for delta y, and then we can plug in our values, resulting in 0.045 meters above the table. In other words, the car would reach a maximum height of 1.55 meters from the ground when it flew through the air. Okay, here's another question for you, Alex. What velocity would the car have when it was moving towards the floor and it was at the same level as the table? You got it, Alex. This question doesn't really require any math if you simply remember that projectile motion involves mirror images, in which the amount of time to go up is the same amount of time to come back down to the same level with the same magnitude as it had initially left. So in this case, the car was launched with an initial velocity of 3.7 meters per second, which means that when it goes up, reaching a velocity of 0, then comes back down to the same height as it was released from, it's also going to be traveling at 3.7 meters per second, but in a negative direction. This concludes our video lecture. Make sure that you took good notes, and that's it. Have a great one.